Hi there, back again for our third edition, or third online edition. Today we have two talks, one by William Woodruff and the second one by Andreas Molzer. And yeah, enjoy, and hopefully we can meet up on location soonish.
All right. Hello, everybody. Hopefully my slides are presenting. I'm not actually sure. Oh, there we go. Okay. Okay. Yes. Good evening to everybody. I'm actually in the United States, but I imagine it's about 8 o'clock there. So um, good evening. My name is William Woodruff, and I'm here today to talk a little bit about a steganographic technique that I've recently implemented in Rust for hiding messages inside of x86 binaries. So I'll talk a little bit about each part of that, both the x86 side and the Rust side. So yeah, on the agenda today, I'll quickly introduce myself. I'll talk a little bit about steganography in general, as well as specifically doing steganography on computer programs. Finally, or next, I'll talk about some of the unique facets of the x86 instruction encoding, some of the things that make it uniquely suitable for hiding messages. And then finally, I'll talk about the implementation that I created, which is steg86, and how it actually works. Yeah, so like I said, my name is William Woodruff. This is a talk that I'm giving independently, not representing my employer, but I work at a company called Trail of Bits. Most of the work I do is actually somewhat related to the contents of this talk. I do program analysis research, mostly inside of the LLVM compiler, sometimes inside of GCC, sometimes inside of dynamic platforms. So a lot of the things that I work on in my day job are tangential to this. And then in terms of open source stuff, I'm a maintainer of the Homebrew project for those of you who use Macs. And then I'm a miscellaneous contributor to many different projects. Yeah, but let's talk about steganography. So most of you are probably familiar with steganography as a general concept, but for those of you who aren't or who want a refresher on it, the underlying concept behind steganography is hiding data within data. So you take a piece of like innocent data, such as a text file or an image or a sound file, and you embed a secret message inside of it that only parties who know how to decode or know the right place to look can find. Critically, because it's about hiding rather than mathematically obscuring, it's not a form of cryptography, and it doesn't provide the same sort of strong guarantees that a crypto system can provide. And because it's contingent on the type of data and the format of data itself, there are different techniques for different kinds. So a pretty popular kind is least significant bit encoding for image formats, especially lossless image formats like PNG, where you can take the least significant bits of an image that are imperceptible to a human, as well as to possible statistical analysis, and encode small amounts of message data in each least significant bit. For sound files, you can do the same thing. You can hide an image in the spectrogram of a sound file, and then because of sort of the massive input space of UTF-8, you can also hide things inside of even plain text files. You can hide things inside of like spacing rules, as well as special characters between different alphabets. So this all begs the question, what about computer programs? Well, it turns out that in a lot of ways, computer programs are a natural choice for steganography. They tend to be very large, especially recently with the sort of trend towards static linking with Go and Rust binaries, which means that they have lots of informational capacity. Computer programs have historically had extremely complex binary formats. If you're familiar at all with the PE, Mach-O, or ELF formats, those are for Windows, Mac OS, and Linux, respectively, Linux and other Unices, respectively. Each of these formats is extremely complex internally. I mean, they have multiple levels of indirection and cross-references between different objects, as well as different like sections within each format that can be laid out in different orders in either the file offset order or the memory layout order when it gets actually dynamically linked in. So there's all kinds of sort of like parameters we can select and modify to hide information within these formats. On top of that, programs themselves are actually written in machine code. And historically, or not historically, but in general, machine code encodings are complex. X86. I'll get into more detail on this, but x86 is an extremely complicated format. The various ARM encodings are less complex, but can be complicated by things like thumb mode. There's the power architecture, which has a relatively complex encoding, so on and so forth. And finally, because computers run programs are present on every computer. And so the presence of a program on a computer is not itself inherently suspicious, which is a boon for us as steganographers attempting to hide a message somewhere. Let's talk about some potential approaches to hiding messages in programs. One thing that we could do is we could, as sort of the compiler controller, we could hide information in the stack layout selection as well as register selection for a program when we're compiling it to machine code. On most systems, you have a stack which contains the local objects for a particular function or whatever frame you're in. And the layer of that stack is determined by the compiler and by the ABI to a certain extent, but mostly by the compiler. And so if you control the compiler, you could say that, a certain pattern always indicates a kind of message. Similarly, all modern architectures have a pretty wide selection of registers, and the register order and register selection is partially controlled by the ABI, but some of it is free. And so similarly, we could hide messages in the order in which we select registers for different operations. Of course, there are two big problems with this. One is that we need the program source, and this isn't always feasible. And the other is that we need to maintain a compiler. And compilers are complex, massive things that are not fun to maintain. So this option isn't especially appealing to someone who's just trying to hide a message. Another option is that we could hide messages in the binary format itself. So I mentioned like PE, Mako, and ELF. These formats have things like a segment list in them, and a segment list has a corresponding both file offset and a virtual address offset. And so we can mess with the order of these things, or we can mess with the order of relocation tables or things like that to hide information. And this is perfectly feasible, but a challenge with it is that it's specific to that particular format. For example, the relocation format inside of portable executables on Windows is just different from that of Mako and different from that of ELF. And as a result, if we wanted to hide messages in a cross OS manner, we have to sort of implement an adapter for each of these formats, which is fine, but it's also maybe not what we want to do in this case. It's not ideal. Yet another option is we could actually rewrite the program after compilation, so we could operate on the machine code directly. This example may not be the best one, but let's say you have an operation like adding -50 to the EAX register. In terms of high-level semantics, that's exactly the same as subtracting 50 from the EAX register. So if you rewrite every negative add into a positive sub, you can encode one bit of information that way, or vice versa, right? It's probably unrealistic for a compiler to actually emit a negative add like this, but you sort of see the concept. But of course, this also comes with other problems. The chief problem is code data disambiguation. This is a fundamentally difficult problem to solve, and it's sort of if you can solve this problem, you can solve large parts of program analysis that most people, I think, are probably impossible to solve in the general case. Similarly, the presence of relocations in binaries as well as position-independent code messes with our ability to arbitrarily replace instructions, especially if those instructions change the length of the binary. If you change the offset by +1 or -1, all of a sudden a relocation will fail to apply in the correct place, or a position-independent move or jump will be incorrectly computed based on the program counter. So that's not ideal. That means we could subtly break the binary in really bad ways. And then finally, there's also the problem of CPU level semantics, like the arithmetic and status flags. Add and sub don't necessarily set those flags in the same way. They might set different ones to different conditions. And so without knowing actually how the compiler expected those flags to be set, it's not actually safe in the general case to rewrite adds into subs or and into some other combination of Boolean theories or anything like that. This is three options. None of them is immediately standing out as like a great one. So my question is like, can we do better? And to talk about whether we can do better, we need to talk a little bit about the x86 instruction encoding. Again, I don't know how familiar people are with this encoding, but at a high level, it's a variable length encoding. It can be anywhere from 1 byte in the simplest case up to 15 bytes in the most complex. It can actually be even longer in terms of semantics, but actual modern CPUs, modern x86 CPUs won't accept instructions that are longer than 15 bytes. x86 is also extremely complex internally. It has about 50 years of backwards compatibility baked into its encoding. It has multiple overloaded fields that have different semantics depending on the mode that the CPU is in, or how another previous field was decoded. So it's not a trivial format to decode on its own. And also, because x86 is not a load store architecture, it has multiple rich source sync combinations. So instead of every ALU operation being register to register, you can have register to register, register to memory, memory to register, immediate to register, immediate to memory, and then probably some others that I've forgotten. But the point there is that there's a lot of complex encodings that can be used to represent the same fundamental machine semantic against different operands. And this diagram below is just a small fragment of that format. But for our purposes, we want to think about one specific part of that format, which is the part called the mod RM byte. And you don't have to know that much about this. You can essentially think of it as an 8-bit lookup table. It's a byte, so it's 256 possible options. It's historically how x86 has encoded operands to its instructions. It doesn't cover all of those operands just because x86 is complex, but it covers many of them. Specifically, it covers 1 or 2 operand encodings, where the operands are either register to register, register to memory, or memory to register. So as you can see in this layout below, there's this mode section of the field, which determines the addressing mode. There's this reg opcode mode, or reg opcode field, which is either a register mask or an opcode extension. You don't have to worry about the opcode extension. And then finally, there's one last field, which is this RM field, which is either a register mask or a memory addressing mode. So as a result, the mod RM byte can actually encode those 3 different modes that I talked about: memory to register, register to memory, or register to register. So let's talk about one possible one example of that. One real example of that. A real example of that is the XOR opcode in x86. And you don't have to know x86's instruction syntax, but essentially what this opcode table column says is the XOR opcode starts with 31 or 33, and then /r means that it uses the mod RM byte to encode its operands. And so these are 2 different variants of that XOR instruction. One is XOR RM32 R32. So that means XOR a register or memory operand with a register operand. And then the other one is XOR R32 RM32, which is XOR a register operand with a register or memory operand. So there we have our 3 combinations. But actually, I said 3, but it's really 4, right? If you look closely, if you remember that register RM is either register or memory. So in fact, there are actually 2 separate encodings of register to register XORs in x86. You can either do 31 register register, or you can do 33 register to register. So for example, 31C0 that should be XOR instead of MOV. Whoops. 31C0 is XOR EAX EAX, but 33C0 is also XOR EAX EAX. These are semantically identical. They're the exact same size, so 2 bytes. And even in 64-bit mode, which I haven't even covered yet, I've only been talking about 32-bit mode. 64-bit mode is its whole own world of complexity. But even in 64-bit mode, this invariant holds of them being the same size when you include the rex prefix, which just isn't that important to us. So what we actually have here is we actually have a single bit of information, right? The encoding that we choose for the semantically identical machine code semantics represents 1 bit of information. And with enough of those, we can actually hide entire messages. And so critically, this is entirely binary format independent. We don't need to worry at all about the underlying or the overlying Mach-O, PE, or ELF container that the binary is in. We just have to extract the text section. And so consequently, Steg86 internally uses Goblin, which is this really cool binary format parsing library to just unpack each of these formats into its text section. And like I said, the encodings of these duals are the same size, so we don't have to worry about position-independent code or relocation commands being broken, because the relocation command will just swap the same field. There's no offset change. And similarly, just like Goblin is this fantastic binary format parser, there's this fantastic x86 instruction encoder and decoder in Rust called iced x86. It's actually extremely complete. For those of you who aren't in the program analysis field, it's relatively rare to find a high quality encoder like this. And all told, this only comes to about 700 lines of Rust, most of which is this large table that it uses to drive the encoding and decoding processes. And it all gets wrapped up into this nice command line interface called steg86, which has these 3 subcommands: profile, embed, and extract. So I'll go into more detail about the actual implementation here. Like I said, steg86 takes advantage of these semantic duals. It turns out there's a whole bunch of these. On top of XOR, there's add with carry, subtract with borrow, and XOR, move, and compare. Each of these internally has 4 variants, not really, it's actually 3, but 4 variants technically. And each of those 4 variants gives us 1 bit of information. We have to subtract a little bit of a few bits just for a header so that we can keep track of the actual size of the message and everything. But all told, basically for every potential dual in the program, we get 1 bit of information. And as you can see with this steg86 profile run below, we can actually get not a ton, but a decent amount of information capacity out of a random off the street binary like bin bash. So that's not bad at all for just a little bit of work. Yeah, and so this is what that actually looks like. Inside of steg86, there's this big table called semantic pairs, which is just an array of tuples of code to code. And each of those tuples is a pair of the RM to register encoding muxed with register to RM encoding. And so each of those represents a tuple of false and true. The false bit versus the true bit, false value versus the true value. And so I've only shown add here for brevity, but there's add, subs, and so on and so forth in steg86 itself. Then, for every instruction in the program, we just do this using the ICE decoder. We check the instruction's code. If its code is not one of the support opcodes, we continue because we can't instrument it. Similarly, the code itself doesn't encode the operand types, so we have to check the operation kinds, op0 and op1. If those aren't register, then it's not one that we support, so we continue. But if we've passed all of those, then we know that we visited one of our possible semantic duals. So we just save its instruction pointer, which, because it's in the text section, it's just the offset into the text section currently. So this is how we actually build up an informational profile of the program. Then, for embedding, we just take that informational profile and we loop over each of those selected offsets, those program counters essentially, and we say, find a member inside of the semantic pairs that corresponds to that opcode. And if that opcode, if we find one, there's a filter ahead of this that actually gets rid of ones that don't match. So this find always succeeds. If we find one, 3 things can happen. One is that it's already in the bit flip, the bit position that is correct, which this might be a little bit hard to read, but basically we say bit here is the bit of information that we're encoding, and then tuple 0 is the false value, and then old code is whatever the previous opcode was. So if we're encoding a false or a true, and we're already and we already match false, then we're already correct. So we can continue. Otherwise, if we're encoding a false and we don't match false, then we need to encode it as false. And if we're encoding true and we don't match true, we need to encode it as true. So that's tuple 0 and tuple 1, respectively. So as a result, we get this new code variable, which we then compose into an instruction. So we basically just say, create a new instruction with reg, which is just the iced x86 way of saying, give me two operands. And we say, here's the new code. Here is the op0 register from the original code. And here's the op1 register from the original code. Take that new instruction, pass it to our encoder object, which I haven't shown just for brevity. Give it the offset that we were at. And then take that data, which is in that encoder take buffer, and just throw it right back into the text section where the original instruction was. And I've snipped out some code there for like sanity checks, like the instruction is the same size. That should never fail, but it's just there for completeness. But essentially, this just one at a time replaces every instruction, every semantic dual with its appropriate counterpart in the program. And the results of this are, we can find messages in x86 binaries, like I said. And here's a side by side of that. You can cargo install x86 right now and try these exact commands. You can, put a message in a file, x86 embed a file, give it an output file, which is test.steg in this case, with standard input as its input. And then you can use x86 extract to pull that message back out. And this works for both, for all of PEs, MACOs, ELFs, as well as raw binaries. So you can think like ROMs, for example. This will also work for them. So there's plenty of other next steps too. There are other tricks inside of x86 that can be used to hide information. One of them is that the test and exchange opcodes are commutative between register to register encodings. So test EAX EBX is exactly the same as test EBX EAX. So if you choose variants of those, you can hide information there. Same thing happens with exchange. x86 also has multi-byte NOPs for alignment purposes within cache lines. And so in the longest case, I believe a multi-byte NOP can be up to like 9 or 11 bytes. So you can actually hide like 5 or 6 bytes of information, which is quite a lot compared to the single bits that we're getting before within just these NOPs. But I should also talk about deficiencies. x86 has a few deficiencies. One of them is that because it operates on the text section, it runs into the problem of code data disambiguation, like I mentioned with the rewriting example way back. And like I said, code data disambiguation is actually just impossible in the general case. We're pretty confident of this. Program analysis as a whole are pretty confident that this is impossible. A large number of open problems are reduced to it. And there are plenty of partial workarounds to it, like CFG recovery and jump table identification. But for arbitrary binaries, it's probably impossible to do. The other big downside of x86 is that it's extremely easy to detect. It's not deniable at all. Compilers do not emit binaries that look like x86 binaries because compilers will only ever choose one specific encoding, not flip between them like x86 does. So if you want to use it to actually if you want deniability, x86 is not going to give you deniability. It's more like a cool trick to show you what x86 is capable of. Yeah, thank you. I realized that people were messaging on Discord, so I'm not sure if they were asking questions or not, but I'm happy to answer them if people do have them. Sorry, Bernard, did you say something? You're muted.
Yes, that's a classic one. Thank you very much for your awesome talk.
No problem.
I actually have a question regarding LLVM. Does it have a bias towards one or the other version that it normally uses versus the one you replaced in? And then could you detect if something was tempered? Yeah, was tempered.
Yeah, precisely.
Okay.
Yes, you could. So yeah, LLVM has a bias towards, I believe, the RMR encoding. So it always prefers to do register memory to register.
Okay.
So yes, if you hide a binary, if you hide a message using x86, someone will immediately be able to determine whether or not there's something weird going on. I mean, the binary will be exactly as fast and operate exactly normally, but it won't look like a normal binary.
Yeah, if you take statistics over your actual instructions, then
exactly, yeah.
Okay. Cool. Very cool. And there are a couple of statements, but not really a question right now. So, how did you find the Goblin usage experience? I visited that crate 2 years ago, and I
thought it was extremely easy to use. Yeah.
Okay. Cool.
Yeah,
awesome.
I have a little bit of experience professionally using it too, so it's one that's really pleasant to use.
That's an advantage. That's an advantage.
Yeah.
There's one question: how much data could be maximally be hidden theoretically?
Yeah. Theoretically, okay. So that it really does depend on the binary, but one sort of fortunate thing for techniques like steg86 is that the trend towards static linking means that binaries are much larger than they used to be. So for example, Go binaries tend to be pretty massive. They tend to be multiple tens of megabytes. So you could probably hide image files, maybe even a music file, on the order of tens of kilobytes to maybe hundreds of kilobytes in a multi-megabyte file. The ratio is really small just because it's single bits at a time, but the bigger the binary gets, basically, the more information you can hide. And this is actually especially true for Rust and Go, and especially Go, because Go's compiler is a little bit stupid and emits a lot of like mobs and ads where it could optimize them into like SIMD or something similar.
Okay.
Yeah.
Another one is like that the original paper mentions like 1 in 100, like you can store 1 bit in 100 or hide 1 bit in 100.
Mm-hmm.
What was your experience regarding that?
Yeah, so I got roughly the same numbers. The original paper is based on x86 32, and then I also evaluated x86 64. And because x86 64 has just more possible encodings, it has one additional possible dual for each opcode. I was able to hide a little bit more, but I think the ratio remained roughly the same.
Mm-hmm. You said that the move instruction also had a dual.
Mm-hmm.
So technically, I'm not sure if you heard about this. I just learned about it this week, I think. There's the Mobfuscator, I think it's called.
Oh yeah, Mobfuscator by Christopher DeMoss. Yeah.
Yeah. So it essentially like replaces all your instructions with move instructions, because technically move is Turing complete.
Mm-hmm.
So everything else is just an optimization. So technically you could like push your bitrate to 100%. Like like every instruction can essentially encode one. Your binary might be very slow then.
Yeah. Yeah. Mobfuscator is actually a perfect example of that first technique I talked about, where you actually control the compiler, because they built it on top of a compiler and were able to do instruction selection to just only mobs. Yeah, Christopher DeMoss has a ton of binary analysis work that's related to this stuff. He also has a tool called SandSifter that does differential fuzzing of x86.
Okay, I didn't know about that. Maybe you can post a link to that in the Discord.
Yeah, I will definitely do that.
And okay, thank you so much. I'm gonna tune you out now. And yeah, see you.
All right, bye-bye.
So our next talk is gonna be in the same realm. Like it's the foundation of like one of our previous talks, like the talk in the Rust remote number 2. They restored data with the image crate, and today we have a talk about the image crate by Andreas. I think you're still muted.
Hi guys, thank you very much. Yeah, so I was a bit conflicted what I should actually present, and so this is about image, the crate, and the organization, and all of the other crates that are part of the image crate itself. Yeah, this is more of a community outreach, let's say. So if you have any questions, just write them in the chat. I will try to even pause the talk at relevant points and try to answer them if it fits, because this is more of an overview and engage with people, etc. So yeah, so who am I? Yeah, you find my GitHub, and you can also reach me on Discord, ping me anytime. My own libraries, which I could have presented as well, but some other time, which you might know me from, but mainly image nowadays. So the main purpose of image of the library image is to make image I/O easy, fast, and safe. So basically the 3 core concepts that Rust provides and is perfect for. Easy because it's a high-level language, fast because you actually get a compiled language and you have good optimization, and safe because you have memory safety. And especially the last point is something that a lot of other image libraries are missing. I think If you've ever done something with image magic, then you might know that it's somewhat infamous for its security bugs. There's a ton of CVEs for it. It's still used everywhere, from PHP servers to anything you can think of to do image computation. Yeah, so that's something that we want to change. We also found that everyone writes their own image decompressors. Like GTK has one, WebKit has a different one, and all of them are not quite correct. All of them with different bugs, all of them in C, so all of them unsafe. Now all of them are fuzzed, and Google's fuzzing project still finds bugs. Yeah. So Rust should change that, if possible. Yeah, so how can you use image? Here's a two-liner. You open an image, you save an image, and image, the crate does everything in the background, deals with the formats, and whatever format the path extension determines gets loaded and gets saved. Yeah, and this works with a lot of formats. There you see all of them that we currently support. I should say the footnote that's not visible on the slide means that not all of them are supported equally well. So PNG, JPEG, GIF, and BMP all work reasonably well. All support pretty much everything that the standard offers, except some semantic information, but the format itself is decoded, and the image vector is perfectly fine, I think, or it should be. And then it slowly gets a bit worse on the feature side. So eco, I think, is only decoding. Yeah, TIFF is, we're getting big TIFF support someday soon. But I wouldn't say it's a complete replacement for libtiff. WebP doesn't do color. PNM is actually quite good, but most people don't use the NetBPM formats anymore, I think. It's mostly for some research, research images, and the NASA does some stuff with it as well. Mostly on the internet, you use PNG and JPEG. And yeah, DDS, TGA, someone contributed a partial decoder and an encoder, so we have that. If you've never heard of that, don't worry. It's bisectless, so it's in totally trivial format, but no worries. Yeah, so how did this actually get started, this project? So I wasn't originally in that project. In 2014, Envin and B. Sweeney started the project as part of the Piston game engine. So it was actually the main API didn't change much. For decoding and encoding was the same idea. Build image decoders, and because it was a game engine, of course, they needed to load some textures. And then we started, built PNG and JPEG in basically a few months or weeks even. Yeah, and then the maintenance started and feature support. Yeah, then in 2016, the image project crate got separated. The difference is that ImageProc tries to actually do some interesting operations. So basically, if you come from the Python ecosystem or have heard of it, then ImageProc is somewhere between NumPy and Pillow. So Pillow can do some semantic stuff. The image crate itself can do a little bit, but mostly because we haven't moved the interfaces around. Yeah. And in 2018, then yeah, I joined with large fixes to PNM because I needed that for university. And then in 2019, we split the crate up because B. Sweeney wanted to focus on Piston. And then, yeah, the choice was just active contributors. So I took that role as a maintainer of the library, and oh boy, I wasn't quite ready, but I think it's fine now. And now 2020, we finally got a good version down. We started to stabilize some things. The interface doesn't change as much, and I'll come to that in a little bit more detail. So yeah, what do I mean with stability? So here's an overview of the minor versions for each major version of the crate. So 0.4 had 3.3 had 15 minor versions before the bump, and then you see a lot of versions with very few minor versions, where the interface changed a lot. That was because the interface was mainly motivated by Piston, and the demands for the Piston game engine changed a lot. So everything broke all the time, basically. And then you see some stable versions. And what's interesting, if you look at the number of dependencies, so crates that depend on image, and if you look at their versions, you see a clear correlation between the two. There's still some libraries that depend on 0.12. I wouldn't recommend that, but someone still does. And you clearly see all the little spikes. And then now 0.21 had quite a lot of minor versions again, and we really started to try not to break the API. Sadly, we did have to do some fixes for safety, but I think we're getting to a good point again. And dependencies also clearly, most dependencies now depend on newer versions of the code. But the main thing is, if you're doing a library as used or with a variety of image, people will depend on the old versions. Like, there's nothing you can do about the people or crates that depend on 0.12, and who knows how many people actually use that code. According to the download stats, it still gets over 3,000 downloads per month, which is horrifying, actually, because I don't want to know what kind of bugs lurk in 0.12. But yeah, that's the main reason for stabilization, for keeping an interface that's maintained and that gets upgrades. Yeah, so who actually contributes to image? There is no strict leader. I don't know of anyone who does it as a full-time thing. Most of the contributions are from people who are interested, who are missing some feature, and then basically providing a new feature as a PR, as their initial contribution. That happened for TIFF, that happened for PNG, or for animated PNG as well. That happens all the time for all the formats. And we also have some researchers who contribute stuff. They're mostly interesting because they tend to stick around a bit longer. But because of this loose group, the policy is, if you push any feature, if you complete any feature PR, you get an invite and you have push access. So any contribution after that is much easier. There's no formal policy for sign-offs. The only thing is that only me and Fintelia can actually do releases of the crates, and we obviously vet the PRs that got completed from one release to another. Yeah, so now let's talk a bit about the design of the image. It's totally simple, right? You have an image buffer, you have some bytes, the width and the height. Yeah, sadly not. Sadly, that's really not the case. It's really subtle. So this sort of structure gets used a lot, I think, especially if you do some ad hoc image buffer. I mean, it works. If you don't need any compatibility, it's great, actually. But sadly, it has some negative points as well. So the main thing is it's platform dependent, incredibly platform dependent. on some platforms you can only support 16-bit width images, of course, and if you use that as your buffer, it's fine. But if you push that into the interface and can only support reading PNGs that are actually 16, no, wait, actually for PNG it's fine. TIFFs, for TIFFs it's a bigger problem. But if you can only support images with 16 bits of index space along one of the directions, then you're missing a lot of images. So mostly medical images, etc., tend to be a lot larger. And an image that's much larger than 65,000 pixels is not that big yet. And now it's even getting into the space of computer screens, right? At 4K resolution, we are not that far off. And if you're putting some monitors together into a huge display, then you can forget 16-bit. Yeah, but of course, U size is fine. Mostly you're going to be 32, 64. But the bigger problem is actually that the byte vector cannot represent any byte data well, because as you know, or as you might know, in Rust, structs need to be aligned, and because vector control the vector, the internal library type vector controls the allocation, you can't control the alignment of the bytes within that vector. So if you want to have U16 as your channel type, if you want to store 16 bit depth of information, you need to be careful, because the bytes that you get from the vector are not guaranteed to be aligned for that, and you can just write your 16 bits as a U16. And also, yeah, in the design, there are no invariants. You can't really control the size of the image. And one subtle thing that you might miss is that if you multiply the width and the height, you might, of course, exceed the length of your vector, but wrap around so that you fit into the vector, and then you're going to have panics at runtime if you access them far out, some pixel far out. Yeah, you're going to be sad. So let's try another struct. Let's do basically the most flexible option you can think of. Yeah, right. You have a buffer that is user supplied even. Yeah, so no vector business. Now you can just supply your own buffer, and then just a layout descriptor. And the layout, yeah, we have some fixed integer as the sizes. So if we switch platform, we can do the size comparisons correctly. But the strides are in memory, so the strides are U size. But now we have a different problem. Now pixels and channels can alias. What that means is if I use a channel stride of 0 or a width stride of 0, then each of the pixels ends up in the exact same location in the buffer. And that's not good for Rust, because Rust's mutable pointers need to be unique. And if all pixels end up in the same spot, they cannot be unique. So suddenly I cannot give out mutable references to pixels. And there's another reason why I cannot really do that, is you can't trust buffer. So mostly what you do is you either require some implementation of asref, so you dereference into a slice, but this implementation isn't unsafe. There is no unsafe guarantee that you can rely on. This implementation could give you a buffer that changes in size every time you access it, for example, or an implementation where that does some I/O, and yeah, you just can't rely on that buffer. So this is mostly good for FFI purposes. So this is compatible. You can access this from any language if you use the right buffer type, but it isn't really useful for an internal type. So then type safe option is next, right? We had the problem we can't trust buffer, so let's use our own buffer again, but actually we need to use our own type for the elements as well, because otherwise we had the problem of bytes. Okay, so how does this look? We have a pixel type trait, and we have an associated type. And inside our buffer, we use the pixel type and its channel type as the data type of the vector. So now the alignment issues are gone, right? If we supply the type channel as U16, then the vector is correctly aligned. We even have the right element type, so no casting. Everything's fine, right? Yeah, no, still not. Because now we have a different problem. Now we are too open in the type. If we want to access that data and store it somewhere, mostly that interface takes a byte slice. And problems with byte slices is they must be initialized. And we have only this type, and the type may contain padding. And if it contains padding, then it contains uninitialized bytes. And if we now grab an initialized slice, we have violated a property of Rust, and we can't do that. That issue actually appeared in another crate, in the RGB crate, where this was suddenly introduced, and yeah, so they had to work around that issue and maybe break some stuff. I hope not. I don't think someone seriously used it, but it's a potential soundness hole. Yeah. And another problem that we now face, because our vector is now dependent on the type supplied by the user, is we can't just relocate that vector. So if we want to reuse the memory allocated by the vector, and keep in mind images tend to be large, so that might be gigabytes of memory that we might want to reuse because we don't just want to throw it away, we can't, because the allocation of a vector needs to be specific to that type's alignment and size. And if we change any detail on the layout of the type, we need to allocate a new vector. At least that's what the standard library requires us to do. Because the allocator might use the alignment information for a different allocation or the size information, and we just can't control it. And if the vector deallocates itself because it's dropped, then it uses that safety information. Yeah. So sadly, no buffer reuse here, or no trivia buffer reuse. And because images type actually looks like this, we have that problem today. Yeah, but breaking it would be a large breaking change. So that's just the problem that we have to deal with. So a quick thing on memory model as well. In Python, you can do nifty things with arrays, with multi-dimensional arrays, that you can't really do in Rust. So the one thing that works fine is if you have a very, very long vector, okay, it's not that long, but you want to slice this up, then you can actually grab mutable slices of both halves. So you can split the buffer in two and grab mutable slices to both halves. And in Python, this works for any multi-dimensional matrix as well. If you don't know what this code does, so it allocates a matrix 4 by 4, and then it grabs the 2 by 2 matrix at the top left. Works fine. You can grab another matrix, and you can mutate everything. But in Rust, you have a problem. If you write this same code in Rust, so let's say we have some type that somehow gives us a row major matrix 2D, so we know the layout, and then we want to grab a slice of that. So the first problem we run into is we need to have some type that we can reference, because we want to have a reference in the end. But what should we actually reference? And here the problem is that reference must point to contiguous memory. So in the slice case, there was no problem, because in the slice case, every element is directly after each other in memory. But in the row major matrix case, that's a problem, because the row major matrix, you have the first row, and then you don't want to reference some elements, and then you go into the next row, and again you want to reference the first two elements, but then again not everything else, and you have a gap there. So what do? You can actually represent it as a type. At least not yet. And similarly, the splitting also doesn't work, because for the splitting you would also need references, and you have this disjoint case where the buffer is not contiguous, and you're quite sad, and you would need to write a lot of unsafe code. Yeah. So if someone would actually do this, and we could, like, as a community, really vet this crate and make sure it works like a reference, but actually isn't, that would be awesome. But right now, I think it would be a huge risk, because, yeah, why would you trust that? It's easy to trust safe code, but trusting unsafe code is quite a daring task. And for a library with as much diverse consumers as image, I don't think it would really fit directly in there. If I missed something and someone has already implemented this, please tell me, because that's something I am desperately looking for. Yeah, but sadly we can't. So in image we did the simple choice, and the buffer is the width and the height in a vector of data, with the trade-offs I discussed before. The good thing is this: the types are platform independent. Here, the width and the height types. We should be good for the next couple of years, with actually requiring a U32 for width and height here, even though some formats support theoretically more. I don't think we'll actually need this in practice. Yeah, and then we avoid naming that type in the interfaces, or in the compatible interfaces. So, for example, image decoder just takes a generic byte buffer, and it tells you how many bytes need to be in that byte buffer, but it doesn't require you to allocate one in a specific way. This was previously not the case. So previously it would return you a vector, but that would already allocate data. It would require you to use the allocator vector, and that's quite inflexible. Yeah, so you pass it in memory. One thing that might be surprising here is that you must pass all of the memory at once, but that's actually required to support all the formats that there are, because ultimately the image format decides in which order all of the pixels are stored and how. And to deal with all of the different layouts that would be possible to support and to read efficiently isn't really helpful. So for all of the cases where this is complicated and can be done in an efficient way, there's a specific crate, for example, PG or TIFF. And if you want to read strips one at a time, because you actually can't allocate all of the image at once, we must currently ask you to use one of those crates directly. There are some rough ideas how we can do this to read a sub-image, and it works for PNG, but it's not really pleasant. Yeah. So let's talk a bit about quality assurance in the image crate. Now that we're stable, right? Everything must get better. And actually that's the case. So since April, the PNG crate got a lot of performance improvements. Yeah, mostly because the interface is stable, and if you don't have to worry about the interface, you can do a lot of other things. It's just bandwidth that you can use for other implementation, and one of those is of course performance and correctness. So the first dip is just some auto vectorization. We optimized some loops. And then the large dip where everything got better is actually we switched decoder. So previously the decoding library was quite old, and if you followed compression, then you might have heard of mini Z oxide. And basically, we just switched the crate out. Was like a few hundred lines, actually 200 lines maybe, of glue code to not break too much, and then everything just was much better. So in the best case here, we actually got triple performance just from that switch, which is quite nice. Yeah. So I also said we want to do correctness. How do we do correctness? Actually, it's not really easy. So the current approach mostly relies on decoding images for which we know the result. And because images are large, we don't store the whole result. Instead, what we do is we have an image to decode and to decompress mostly. And we only compute the CRC once, and then we just CRC the image data and compare it with the reference result. And for cases where there are expected errors, of course, you also want to test the bad paths, the error paths. We just store some error information. The only problem with that is relies on perfect reproducibility. So first, if you want to have some flexibility decoding, like say, let the image decoder already use scaling of values because it just doesn't use as much memory, and might also get you speed. Then you need to do this for all of the combinations that you want to test. And if you want the image crate to already do some color conversion, then you need to ensure that this color conversion is either perfectly specified or not lossy. Because if it's lossy, then the results might change in subtle ways. If you speed up some algorithm, some lossy algorithm, you might change the result, of course, because that's one of the freedoms that the lossy algorithm gives you. But you can't use the CRC anymore to compare. So actually what the JPEG crate does is it compares the images in a rough way, so it leaves some room of 1 or 2 bits of imperfection. I don't really trust it, but it's the best we came up with. Yeah. And the big problem is, of course, collecting test data here. Because for PNG, there's PNG suite, and it's large. It has even additions, basically covers all of the features. And we use all of that, passes everything works perfectly. And that's actually a lot of testing. But for JPEG, the issue is much bigger. For JPEG, we did not find such a complete set of reference images. So for JPEG, it's mostly images we found or we know we can use for that purpose. Yeah. So for those crates, we have to rely on other quality measures. So in that case, mostly on fuzzing. So Cargo Fuzz is an awesome tool. You should use it. You should use it now. You should apply to everything, except the cases where you can control the input. Yeah, and it should be clear that memory safety doesn't mean panic-free, because that's probably one of the first things the fuzzer will find. You think everything's perfectly memory safe, nothing can really have some security bugs, but no, of course, this is not the case. And memory safety just means that the program behaves in a sort of deterministic way, and that all of your bugs are shallow. So most of your bugs will probably turn out to be panics and no security bugs. Oh, I see I missed a question. I'll try to get back to it after the talk, or when there's a good time. Sorry. So I won't remember that. Yeah, panic-free. So you will panic but actually there was the case for all of the image crates where we apply fuzzing. Basically, let the fuzzer run for a minute, and it already finds 1 or 2 panics. And that's mostly my experience with other targets as well. It's pretty easy to convince yourself your crate does everything correctly, and it doesn't. Especially if you check for integer overflow and you want to have explicit integer overflow, you're gonna have to do a lot of subtle fixes. And one of the hard things is that the fuzzer is also not perfect. So it might find some cool things at first, but to actually get good coverage is hard. For some of the image libraries, there are pre-computed data sets that are basically interesting images that try to elicit as much behavior from the decoder as possible. But doing this for a new image format takes a lot of time. You have to do a lot of fuzzer runs to get there. And if you don't have a good corpus, your fuzzer run will be less significant. So it might tell you everything fine. It ran for days and didn't find anything, but there might be 1 or 2 conditions that or 1 or 2 code paths that it didn't check. Yeah. And it can't guarantee you that it checked everything. Keep that in mind. So the good thing is that fuzzing is also useful for a lot of other stuff. So one of the coolest things is that it's good as a refactoring tool. And that might be surprising at first. But what you do is you basically do model checking. You have some known good input or good pair of input and output. And if you do some changes, you basically tell the fuzzer, do the same algorithm, and if the data comes out differently, then panic. And then any panic that you get means your output isn't correct. And that's really, really cool. If you see that in action and you do some decoding algorithm, you check that the output actually matches the expected output, the fuzzer will find most bugs really, really fast. Or most easy bugs at least. And this is actually very useful in refactoring because it gives you a really nice tool to check automatically in background if there are still some inconsistencies with the old output. And in one of the cases, it actually, where we applied this in image for decoder, it actually found some edge cases where we didn't actually consider what output we wanted. Yeah, so we had to specify that first. But one of the cool things is that it also avoids copyright issues. The fuzzer builds the corpus from nothing, or from some initial seeds that you know are good in terms of copyright. So everything that it finds, it has generated itself. So you can be, I'm not a lawyer, so don't trust my opinion, but that's my opinion. You can be basically sure that what the fuzzer produced doesn't belong to anybody. If you want to. I mean, I'm pretty sure that there are some lawsuits that actually said that the completely automated tool, the output doesn't belong to anybody, but not the thing I want to think of, the law there. But this also helps refactoring, because if you have some bug and you can't really reproduce it, but the fuzzer finds it and finds you a good test case, then you can also reduce that test case and try to make it as small as possible. And then you can use that automatically generated test case and actually commit it to the repository and be assured no one will come and say, hey, that image that belongs to me, now you must take down the repository because Git inserted that image into a Merkle tree, and good luck trying to get rid of it. Yeah. And final bit of tooling, because it came up a bunch of times, Rust format. I would like to say the Rust format is the best tool for Rust formatting, but sadly I can't. So VS Code automatically does Rust FMT, I think. So every time you save, it neatly formats the file for you. But sadly, it really isn't compatible with introducing to an old project. So there you can see an image of a picture of a closed PR for doing a complete cargo FMP run. And on all the code, and you see it's 3.7K lines of changed code from a single run. And weirdly, there's 1.5K new lines, so lines that the formatting inserted that weren't there before, because you can imagine how the code looks. It's just basically one huge chunk of new code. So in that case, I think a few of the functions have a lot of parameters. Changing parameters would be an interface break, which we don't really want to do right now, as I said before. But to get cargo FMT to actually format that nicely, we haven't found a way to do it. And currently what it would do is basically break every single argument into a new line. And that introduces hundreds of lines. And also it doesn't correctly interpret some license header, I think. And at some point it tried to format a license header, which is a shame, and I mean that we can have that. And 1000K two new lines, I mean, who wants to review that? Not as a PR, I mean, we could apply the tool ourselves, but it would also break everything that's ongoing, because it touches every file, basically every line, or every other line, and chances are high if you change some other thing concurrently, it's going to break, and you need to rebase. And normally rebasing is fine, but rebasing with actually many merge requests, merge conflicts in that case, because the line changed in both branches. Yeah, so for now, what we try to do is we introduced it to the newer crates, so the smaller crates, and there we have some tooling, automated tooling. But for the old image crate, we haven't made it work. What's really the problem is you can't selectively enable options. Like if there was an option to say only do whitespace formatting, only remove whitespace from the end of lines, only make sure that alignment, tabs, and spaces are correct, etc. That would be really cool, because that would mean that the PR would be merged in more time. That's the easy thing to do. But since there are so many options and all of them are enabled by default, there's no switch to disable them in many cases, or to have some leniency. For example, if you specify a column or a line length, then everything must fit to that line length. And if you break lines before the line length, then it will try to merge the lines. And if you break them after them, then it will break them into separate lines. But in many cases, there is no fixed line length. Like for some code that's very easy to understand, it's cool to have a long line, because say your names are actually that long. But in other cases, you don't want it. And to mix the same two styles in a single repository just is impossible with Cargo FMT. So, yeah. If we find a solution at some point, it would be cool. Yeah, so let's come to the not yet some part. So the biggest issue is arbitrary memory use is easy, because Rust makes it easy, but it's a huge denial of service risk. I didn't want to fit anything else on the slide, because that should be the thing you should remember. Rust makes it incredibly easy to use memory. You write back, and you give it some initial element in a huge size, and Rust just goes ahead and tries to allocate that for you. But if the size actually turns out to be 2 to the power of 60, then your program panics. And now you can easily imagine an image that just pretends to have a large number of pixels. And if you read that and go ahead and allocate memory for it because you're diligent and you actually want to read the image, then you do a huge allocation, and boom, the whole process gets killed. or the thread, neither is really good. So that's a problem, because most of the standard methods don't really care a lot about allocations. Even sorting allocates memory for you in the background. So sorting a very, very large array means a very large allocation, silently. And that very large allocation can fail and trigger the panic handler for the allocation. And sadly, there are very few crates, or very few stable crates, as was the standard library, that really try to deal with that and make it more manageable. Because, yeah, I mean, the semantics are clear. You should expect that the allocation works, but untrusted input shouldn't be handed control over your stability. So reading images shouldn't really just do anything that the image format tells it to, because else we arrive where image magic is. Yeah, so sadly there's no single interface that deals with that yet. Only some limits that you could set in the PNG decoder, and you can set in the TIFF decoder. The other problem is it's not really easy to test, right? Because you basically need to do another fuzzer setup. You want to find formats that try to allocate as much memory as possible, but you also need to detect that, and you need to do reasonable limits. Yeah, so nothing's easy. I read that Rust analyzer has a different formatter. Yeah, that would be interesting to try, actually. So I'll give that a try in the weekend or so. Would be cool if it works, because it's also a little bit of a barrier to contributions. Because as you could imagine, if you post a PR and then you get told, oh no, you have 3K lines that you changed, you have to redo this. Yeah, that's a huge hassle as well. Yeah. So the other thing that sucks is color space support. And really I have to be blunt here, because it really sucks. So what is actually color space? If you've never heard of this before, your pixels don't actually encode color themselves. So a value of 0 red and 140 green and 0 blue doesn't mean the same thing everywhere. It depends on the color space, how much green there actually is in the pixel. I'll have an example shortly. But the thing is, you have to use the same color space if you want to move data around or convert between color spaces. And conversion is not lossless, mostly. And sadly, some tasks are easier in one color space, some tasks are easier in another. So for example, blending is totally easy if you have linear color space, because then it's just a linear interpolation. If you don't have a linear color space, as is the case with sRGB, then it's hard. And this means that most of the interfaces actually don't really mention the color space that they use, but rely on one internally. And all of those would be interface breaks and a lot of hassle to actually get right. Because we want to get it right in the first or at least second try. Yeah, so as I said, this would basically break everything if you introduce the color space parameter everywhere, or require that you check it. Yeah, it's not worth it. So what actually can happen if you don't use the wrong color space? Here's an internal issue from us, because we didn't use sRGB or the correct color space in that case. So here's issue 1260. This is the same image, it just gets loaded and re-encoded and loaded and re-encoded, just as in the 2-line example above, at the beginning of the talk, and it gets darker every time. yeah, that's of course not what you want. You want the image to stay the same if you don't actually change it. Yeah, so what happened here is roughly this. So this was a JPEG image. So the JPEGs are in the Rec 609 color space, or it's defined by that standard or recommendation. And decoding converts them into sRGB for our internal use. And then when we encoded it, we must convert it back. And here there was a bug that converted it into the wrong color space. So there's still everything fine if you are in the correct color space. But if you don't tell the JPEG that you use some other color space, or you can't tell it in this case, then the data is just byte data at that point and gets silently reinterpreted, and then suddenly it's another color. And in that case, in the other color space, here it's just a very subtle thing, same color, the same recommendation, but once the definition with headroom and once without. So headroom just means that you don't use some values. And as you can imagine, everything else is compressed. And you only use the values from 24 to 250, I think. Yeah, so if you reinterpret the color, then it gets darker. And that was the issue that was present there. Yeah, and if you do that a couple times, it gets really dark. Or just in that case, it would level out at some point, but it would be dark. Yeah. So, what do we actually plan for the future? We first want to integrate color conversion. The interface for that is inspired by FFmpeg. So we have a plan for that. There's also already a draft for the integration. Basically do what FFmpeg does. Basically copy their interface, their treatment of color spaces, and their constructors, but of course safe, and that's the main difference. Yeah, I hope it works out fine. Just needs a little bit of push to finish, a little bit of polish on the draft. The other cool thing is that's happening. I had some time rewriting the LZW decoder, which is a compression format that's used in GIF and TIFF. That crate was very old, not really maintained anymore, or yeah, not really. Who am I kidding? It wasn't maintained anymore, and it was slow. So rewriting that decoder actually means a speed up, and that should get finished very soon. Should give a speed up of 200 to 300%. So triple speed for some GIFs, and probably similar for some TIFFs, but in TIFFs it's not really customary to use LZW, so might affect very, very few TIFFs that are in active use, but who knows. And for TIFF in particular, there is an active PR to improve the handling of floating point images, or to actually really get floating point images in the first case, for big TIFF and GeoTIFF. And that's pretty exciting because that's actually one of the big uses of TIFFs that's still missing. And I'm very glad that someone had the motivation and put in the effort to really get that working, and to consult with a few rounds of review and stick for it. That's very cool. So if you're a new contributor, where could you help? So one thing we sort of do IFC-like, but even less informal, drafts for all of the big new features like color spaces and exit. So if you want to give them a look, note some points or suggest any improvement, or even clarifications or so, that would be cool. We'll also give a little bit of an oversight or an overview where what features exist, etc. Then optimizations are always wanted. I can guarantee you there are many missing opportunities for optimization. So if you just run a perf on one of the decoders, you will probably come up with something. In particular for JPEG, there's ongoing effort to try to come up with something, because we know the decoder is slow. Well, okay, it's not that slow, but it's pretty slow. And we can think a speed up of 2 might be possible. Yeah, just work. And then, of course, expanding testing and features. So, as I mentioned before, the hard part is actually finding datasets that you can use freely. So, if for any obscure format, like say you have thousands of freely available TGA lying around somewhere for some reason, or animated PNGs. I have some animated PNGs, but let's say they are not really safe for work or uploading to GitHub as test cases. Because guess where most of the images come from that you can freely use, or at least freely download? Yeah, image boards, and particular image boards. Yeah, and JPEG decoder needs some expert help, so we moved the project into image to at least maintain it. But we don't really have an expert who actively maintains it and knows a lot about JPEG. So any help would be appreciated there. So yeah, thanks for listening. Link to the whole organization, actually, you will find the repository just one link away. If you could contribute, that would be really, really awesome. Resource limits are hopefully coming as well. So hopefully draft will finish, and unified color management, sadly not. You'll have to go the long route and use the image-specific or this format-specific crates to get them out of images or insert them. I know for a fact that TIFF can do this and that it works. You get ICC color information, you can insert it, and an example will probably appear at some point. But hopefully, like say in the next year, some better solution comes up. Okay. So, is the encoder lib already public? Yes. Could
you share a link?
I assumed you speak of the LZW encoder.
Yeah, exactly. Yeah.
Yes, I will share a link.
That would be awesome. And another question: did you already profile your JPEG decoder? Do you know which takes up the most time? Which parts?
Yes. Just shortly. So here's the link for the LZW encoder and encoder. It's actually both. Nice. There we do spend some time actually doing Huffman decoding. So that's very likely one of the first points that one could address. So during JPEG, there is one Huffman decoding phase. And in that, we know that this could be faster, probably a lot faster, because currently it's done 1 byte at a time, basically with a table, and that is really not performant at all.
Okay.
But it doesn't. Well, it's not the whole decoding, so I think it takes 15 to 20% of the whole decoding runtime. But if that could be sped up by a factor of 2, you also save 10%, which is rather good. And the other part is probably a vectorized decoder for all of the color conversion that you do, and all of the coefficient matching.
Could you quickly elaborate how a JPEG decoder works again? Like I have it roughly in my head that you essentially, for compression, you use a wavelet transformation, if I remember correctly, or for year, and then you just drop the smallest coefficients. And
not quite.
Okay. close.
I think I'll take it over from there. So
Yeah.
roughly, so you split the image into 8 by 8 or 16 by 16, which is suddenly used, I think, chunks, little small blocks. You do a wavelet transform, as you said, and then you get some coefficients from there. And first you reorder the coefficients into one that ensures that the smallest coefficients are last. And then what you can do in the lossy version is drop some coefficients. So that can be at the end. Mostly it wouldn't make sense to be at the end. And then what you can also do is you split them into different passes. So instead of encoding all of the coefficients in one chunk, what you can do is you encode only the 0th coefficient for all the color channels first. So that makes it easy to get a rough picture, let's say. And then in the next chunks, you encode the first to 8th coefficient. And then etc. In that decoding phase, that encoding of coefficients is done by first doing one transformation to make it compressible, and then doing Huffman encoding over that stream of coefficients. And it's actually pretty complicated because the standard, what it actually says for the decoding phase is there's a little paragraph, and the standard basically says in one paragraph, it's 3 sentences or so, basically do what the encoder did, but in reverse. That's all the information you get for decoding.
So it must be pretty easy then, right?
Yeah, it's trivial.
All right. Yeah, that sounds like more than just a weekend project.
Yeah, I'm
Optimizing
pretty
that.
sure there's some bug where we're missing some color information, but yeah. I want to get back to the other question, I think.
Yeah, does ImageRS support WASM? Like, can you compare it to WASM?
Yes, you should be able to. There was an issue with multi-threading, but I don't think it's a problem with WASM anymore. And you can also always turn it off. So what you can do is multi-threading is only used because the JPEG decoder uses multi-threading or can use multi-threading. And you can just turn off a feature and then everything is single-threaded, and there should be no problem importing to WASM, I think. At least that was the issue resolution last time, and there was no big interface change that would have made that impossible. I missed one during the talk. How many legal inquiries did you already have? Fortunately, none. But that's because we don't have a lot of images in the repositories for testing. So we have basically the standard image test set, which you might know, Codim, and everyone uses that, and I don't know of anyone who gets sued for that. So we have that for most of them.
That was just my
cases,
curious question because you talked about it.
Yeah. I hope that's not so bad. Okay. Yeah. Sven asks, is there any way of iterating the buff in a different order, like y equals 0 to height, then x equals 0 to width? Mutable iteration. Kind of. So for image buffers specifically, let's go back to the slide so that we have the definition. So for image buffers specifically, I will change the screen anymore, I think. Let's fix that. So for image buffering specifically, you have this vector, and what you can do is there's a row iterator. So you can iterate over all mutable rows of data. So if you want to iterate them in different order, you would use the row iterator to get the independent rows, and you can consume the rows in different order. There's also kind of arcane the option to convert it into a flat image. So this is the overblown matrix here, and there you can dynamically assert that the image is a correct image. And then you could basically insert the correct strides yourself and iterate over the pixels that way. But I think both actually have the problem that LLVM don't invite all the bounce checks, which makes me sad, because LLVM optimizes very well otherwise, but for some reason it doesn't elide all of the bounce checks through multiplications. So if you multiply the width and the height to get the last index, and you even make sure that this is a checked multiplication and you didn't wrap, for some reason, if you use that to assert the length of your matrix, it can't deduce that all of the other multiplications that only use numbers smaller than width and height are also within those bounds. But that's the case for both iteration orders, which means you actually have to iterate them in the order of the matrix, so in the data order. And any other order would trip it, and for some reason it doesn't optimize as well, sadly. Does that answer your question? Yes. Did that answer your question?
I think so.
Yes, I would assume so. Otherwise,
Cool.
You can reach me in Discord. So, what's an issue? If for some by chance you have a better optimization, would be very glad. We recently got notified that some initialization code wasn't correctly auto-vectorized by LLVM, and that was then after it was noticed, it was easy to fix. But noticing it in the first place was kind of the deal there. It was quite cool. There's a lot of room, a lot of things you can find. It's not perfect. Kind of the deal with big projects. Yeah.
Cool. Then thank you very much. Thank you very much for giving this awesome talk today.
Thanks for giving me the time.
Anytime.
Yeah, maybe next time. The other day. I have to see how much time I can use to make
Yeah,
the
sure.
shirts.
The next meeting is probably planned for either mid to late October or November. But it kind of depends, because in October there is a new conference, the Rust Lab from Italy. So, and they kind of it's the first year, and they reach out to me to introduce you to it to some extent, and the call for presentation proposals just closed, so the schedule should be up in the next weeks. So I'd like to ask you to keep an eye on that. The topics are supposedly very diverse, and yeah, that's the one conference that's going to be in October 12th and October 18th, and the other one is the usual Rust Fest at the very beginning of November. I think the 5th and 6th of November. So yeah, depending on that, the next Rust Meetup Munich will be scheduled either before that or after that. But let's see. All right. if somebody wants to do a spontaneous discussion or show off some ad hoc live coding, now would be the time. If not, then yeah, I'm gonna be here for another few minutes, and then if nobody shows up, we're gonna call it a day. And yeah, thanks for joining.